if we consider the bond that forms between calcium and sulfur, we remember from grade 9, 10 and 11 that calcium has 2 valence electrons, sulfur has 6 valence electrons, and bonds form in an attempt to reach a full valence shell. So we learned that very simply an ionic bond would form between calcium and sulfur, which essentially involves a transfer of electrons from calcium to the sulfur. As a result, calcium will have lost 2 valence electrons and therefore obtained a charge of 2 plus because it has lost 2 negatively charged electrons, and sulfur has now gained 2 valence electrons and as a result now has a charge of 2 minus. And then we learned that in ionic bonds these substances stick together essentially as a result of the electrostatic force of attraction that exists between these two. This can also be seen as what's known as a redox reaction, in that it is a transfer or a gain or loss of electron of each atom. So we would show here that we have started with calcium, and this calcium has underwent a loss of electrons that leaves it with a charge of 2 plus as it gives off those 2 electrons. We would call this an oxidation reaction. An oxidation reaction because it has undergone a loss of electrons. The original naming was as a result of the belief being that it only happened to oxygen, which it has obviously since been found is not the case. At the same time as this oxidation, we have another reaction taking place, and that is the reaction in which sulfur is gaining 2 electrons to end up with this charge of 2 minus. As a result here, we can see that sulfur has gained electrons, and we call that a reduction reaction. And there is an easy way to remember this, and that is that oxidation is loss, which we can simplify to oil. Oxidation is loss, and reduction is gain, again here referring to the electrons, and that can be simplified to rig. And so the common term oil rig helps us to remember that oxidation is loss and reduction is gain. It is important to note here that these are referred to as half reactions. They are referred to as half reactions because they cannot happen in isolation. It is not possible for calcium just to lose electrons with nobody or no atom there able to gain those electrons. And so we say that oxidation requires reduction because in order for calcium to give off these 2 electrons, we require something, in this case sulfur, that is able to gain or accept those 2 electrons. So they are called half reactions because we require 2 of them to have a complete reaction. Another term that is important in this section is the oxidizing agent. So we know that calcium is undergoing oxidation because it loses its electrons, but it can only undergo oxidation, meaning it can only lose those electrons because sulfur is able to gain those electrons. So we say that sulfur is allowing oxidation to happen, or we say that our sulfur is the oxidizing agent. Once again, we are saying sulfur is the oxidizing agent because it is taking the electrons from calcium, which allows calcium to be oxidized. So therefore, sulfur is enabling the oxidation and therefore is the oxidizing agent. By the same reasoning, we can say that calcium is the reducing agent because in order for sulfur to be reduced, in order for sulfur to gain electrons, it is necessary for calcium to lose electrons. So we say that calcium is enabling the reduction of sulfur. So we say that calcium is the reducing agent. And so once again, We call these reduction-oxidation half reactions because they cannot happen in isolation. You require two half reactions in order for a complete reaction to occur. And what we find is that oxidation is when something loses electrons. Oxidation is a loss of electrons. And reduction is when something gains electrons. Reduction is gain. The table of standard reduction potentials is a useful tool to be used when evaluating redox reactions, and it's important to understand exactly how this table is laid out so that it can be used more effectively. So the first thing that you'll notice is that in the NSC exams there are two tables given, a table 4A and a table 4B. I always encourage people to use table 4B specifically, as it makes it easier to determine whether or not a reaction is spontaneous. What this then means is, if we look at these arrows down the left and the right hand side, is we see that the arrow pointing downward states this is the increasing oxidizing ability, which is often misinterpreted as the ability to be oxidized, where that is not what it actually means. What it means is that it is an increasing ability to act as an oxidizing agent, which is more simply put as increasing ability to be reduced, basically saying that the most easily reduced element on this table is fluorine right at the bottom, and then obviously the same applies on the right hand side with the increasing reducing ability, which actually means increasing ability to act as a reducing agent or increasing ability to be oxidized, which suggests then that lithium right at the top is the most easily oxidized. The second thing that we can see on this table is that all of these reactions are written as reversible reactions, and when read from right to left, so from right to left, we see that it is an oxidation reaction. We see that lithium breaks apart into a lithium ion and an electron, and when you read from left to right, it is a reduction reaction where lithium is now gaining that electron and becoming lithium proper. This table can be used to determine whether or not a reaction is spontaneous, and that is done in the following way. Once you know which reaction is oxidized or which substance is being oxidized and which is being reduced, if they follow this general pattern where you have oxidation occurring and then are required to move down the table before arriving at the reduction half reaction, then that will always be a spontaneous reaction. So very simply put, when oxidation occurs above reduction on table 4B, this reaction will always be a spontaneous reaction and therefore be able to yield a galvanic or a voltaic cell, because those are defined by spontaneous reactions that produce an electrical current. Finally, we will see that there are cell potentials given for each of these reactions. Note that they are half cell potentials. Obviously, that requires that they are all connected to the same half cell in order to measure these, and that is why we find hydrogen in the middle of this table, because the hydrogen, simply put, is declared as a zero cell potential. So then anything that is plugged into hydrogen, the potential that it yields is defined as that cell potential. So we can see that the cell potential for lithium, negative 3.05, and we can read our cell potentials off there. These are all cell potentials at standard conditions, and obviously those can be changed. The cell potential can be changed by changing the factors that affect the rate of a reaction, that being the concentration, temperature, and pressure. So once again, we prefer to use table 4B as it allows us to easily identify a spontaneous reaction, because a spontaneous reaction is any reaction in which you have oxidation occurring above the reduction half reaction, and then you can say that that reaction is spontaneous, and we can calculate cell potential at standard conditions using these given values, knowing that those cell potentials are calculated against the standard hydrogen electrode. A galvanic or voltaic cell converts chemical energy into electrical energy through a spontaneous reduction-oxidation reaction between two substances, one of which is easily oxidized and the other more easily reduced. So the setup that we have here, I have a zinc electrode that is placed in a solution of zinc sulfate and a copper electrode that is placed in a solution of copper sulfate. So the two possible half reactions here are that of zinc and copper, and I would use the table of standard reduction potentials to determine which direction the spontaneous reaction occurs. And we can see here that on table 4b, since the zinc occurs above the copper half reaction, we can say that the zinc is going to be oxidized, and therefore our oxidation half reaction is the zinc solid breaking apart to form zinc ions and electrons. We move down the table then to see that copper undergoes reduction where it gains electrons, the copper ions gain electrons to form a copper solution. And so what we can see here is once that is set up, I've connected this to a voltmeter to detect a potential difference. All that remains to do is to complete the circuit, and that is by using a potassium chloride salt bridge that has been prepared in this U-tube here. And we see that as soon as I complete the circuit, the voltmeter measures a voltage, since there is now a complete circuit, and the salt bridge now acts to maintain electrical neutrality. So what we find happening in this electrode over here where oxidation takes place, we know that oxidation always occurs at the anode. So the zinc is now the anode, and what we can see is that the zinc solid is busy being oxidized and going into solution, which means that our concentration of zinc ions increases in this beaker over here. At the same time, or initially, the concentration of sulfate ions remains constant. In our other beaker, we now have reduction taking place. We know that reduction always occurs at the cathode. And what this tells us is that the copper ions are being attracted to the copper electrode where the electrons are moving towards, and therefore the copper ions, when they leave that solution, therefore the copper ion concentration decreases. As a result, we can see here that since the concentration of positive ions in this beaker increases, we can see that this beaker would become increasingly more positive, while since the positive ions are leaving this solution, this beaker would become increasingly more negative, which is the function of the salt bridge, which we know is potassium chloride. And what that allows is for the ions to flow in the direction that maintains electrical neutrality, which is why we say that the salt bridge has two purposes, the first being to maintain electrical neutrality, the second to complete the circuit. We know that the cathode is always the positively charged electrode in a galvanic or voltaic cell, and therefore the anode is negatively charged. We can also express this in cell notation, which says that the anode electrode is zinc solid, the anode electrolyte is zinc sulfate, the double line here represents the salt bridge, the cathode electrolyte is copper sulfate in aqueous solution, and finally the cathode electrode being copper solid. We can calculate the standard cell potential using the following formula. The cell potential is equal to the half cell potential of the cathode minus that of the anode, which can be read off this table here, and we find that we get a positive cell potential, which indicates that this is a spontaneous reaction, that in ideal conditions, under standard conditions, this should yield 1.1 volts. As we can see on the voltmeter here, it is slightly below that. That would be mainly due to a change in concentration, or the concentration being below what is considered a standard condition. We can also write this as a cell reaction that says that we start with solid zinc and aqueous copper sulfate, which is then converted into solid copper and zinc sulfate aqueous. If one were to leave this reaction for a long enough period of time, we would see the mass of this zinc electrode decrease as the amount of zinc decreases and becomes zinc ions, and we would also see the mass of this copper electrode increase as more copper undergoes reduction and is deposited onto that electrode. And finally, we can see that the electrodes are flowing through the external circuit, that being the wires out here, from the zinc electrode, which is the anode, which is negatively charged. The electrons are repelled from that electrode and attracted towards the positive electrode, that being the cathode, where they then undergo reduction with the copper. Electrolysis is a chemical process in which electrical energy is converted into chemical energy. So the main difference here between this and a galvanic cell, this being an electrolytic cell, is that we are now providing the transfer of electrons with this power source that is forcing the electrons to travel in the direction that we want. So what we have here is we have a solution of copper chloride, that is this blue solution that we have here, and we have two carbon or graphite electrodes. And what we can do is we can, by turning the power source on, we can see immediately that a gas starts forming at the one electrode, and we're going to leave that to run while we discuss some of the theory here. So what we can see is that by connecting a power source to these two electrodes, we create a positive terminal and a negative terminal, where the positive copper ions are attracted towards the negative terminal and the negative chlorine ions are attracted towards the positive terminal. And what we then find is that at the anode, which is now the positive electrode, unlike a galvanic cell, we have the oxidation half reaction, where we can see here that chlorine undergoes oxidation, where these chlorine ions react at the electrode and lose the electrons to form the chlorine gas that we can see coming off here, and obviously lose their two electrons. So that is the oxidation half reaction taking place at the anode, and very clearly we can see that those electrons are being removed by the power source. So they are being taken from the chlorine and then pushed towards the negative electrode, which is where we find reduction taking place. And our reduction half reaction is the reduction of the copper ions as they gain electrons to form copper, the solid. And so what we can see here, if we now take these electrodes out, is we can see that a layer of copper has formed on this electrode, and we can see this is the negative electrode, therefore the cathode, where reduction has taken place. And once again, we can see and smell the chlorine gas that is being removed, or that is being produced by this electrolytic cell. So the big difference here between an electrolytic cell and a galvanic cell, we can see, is that the electrolytic cell takes place in the same container, so that we can have an easy transfer of ions, therefore there is no salt bridge necessary. And then obviously it is very important that we have a power supply unit to move the electrons in the direction that we wish, and it is no longer governed by our table of standard reduction potentials, using that to determine which reaction is spontaneous and which is not. We can now also see that this can be used, or this principle can be used in electroplating, where we now replace the one electrode with something that we wish to plate in copper. Here I have a key, and once again what we are going to see happening here is we're going to see the electrons being forced away from the chlorine electrode and towards this electrode that contains, or that has, the key on it, and at that electrode they undergo reduction, and we'll find a thin copper coating on this electrode. You can see that here, that this key has now been coated with a thin layer of copper. Obviously, in the industry, the anode would be made of the substance that you wish to coat it with, so you usually use a copper or a chrome anode that is oxidized, and then those ions go into solution and then are moved across to the cathode where they undergo reduction. The Chlor-Alkali industry makes use of electrolysis to convert brine, which is a combination of salt and water, or a solution of salt in water, into more useful substances. So like any electrolytic process, this is a conversion from electrical energy into chemical energy. And the way that this is set up in the industry is that we have a single container that is separated by a cationic or a selectively permeable membrane, and we have brine, which is our saltwater solution, pumped into the one side of this container, and that means that there is, in this side, we will find that there is H2O as well as some sodium ions that are present, as well as some chlorine ions present in the solution on this side of the membrane. This cationic membrane means that it only allows cations, positive ions, to pass through it or to move through it. Now what we find is that the way that this is set up, we can see that this electrode over here is connected to the positive terminal of the battery, which makes this the positive electrode, and this the negative electrode. And now what we find is that at the positive electrode, which we know is, in this case, in any electrolytic cell, is the anode, we know that oxidation will always take place at the anode. And what we can see by looking at our table of standard reduction potentials is, with only water, sodium ions and chlorine ions present, the only of those particles that is able to be oxidized is chlorine. As we know, when we read this table from right to left, we are reading the oxidation reaction, which means that we do not have any solid sodium present, we do not have any hydrogen gas present, we do have chlorine ions present, which means that our oxidation half reaction is going to be the oxidation of our chlorine ions, where they form chlorine gas along with 2 electrons. And what that tells us is that the chlorine ions then attach temporarily to the anode, where they lose their electrons, and then what we find escaping out of this top exit is the chlorine gas. We are now left with water being on this side, on the right hand side of the selectively permeable membrane, and because this is a cationic membrane, that means that there's also going to be sodium present, or sodium ions. Now the problem that we have is that there are 2 possible reduction half reactions here. We know that it is possible for water to undergo reduction. 2H2O plus 2 electrons reacts to form hydrogen gas as well as hydroxide molecules. And the other reduction reaction that is possible is the reduction of sodium ions when they gain an electron to form sodium, the solid. And the way that we know which one is going to be reduced is by looking once again at our table of standard reduction potentials, which clearly shows that sodium is closer to the top, water is closer to the bottom, and we know that the ability to be reduced increases as you move down the table, which means that our reduction half reaction is going to be the reduction of water. So what we can see is that at our cathode, where we always have reduction taking place, we have our water molecules gaining 2 electrons to form hydrogen gas, which is then the second product of our Chlor-Alkali Industry, and also then, once this water is combined at the cathode, giving off the hydrogen and also giving off hydroxide ions. Those hydroxide ions would then combine with our sodium ions, which then gives us our third and final product of the Chlor-Alkali Industry, which is aqueous sodium hydroxide. As we can see here, it is then important, with the brine continuously coming in and the chlorine being oxidized while the sodium ions are moving across, it is important to continue circulating out the excess water so that you can continually increase the concentration of brine here, while continually pumping in more water in this side and removing the sodium hydroxide. We can see here that the net ionic reaction, meaning without spectator ions, is then 2 chlorine ions react with 2 water molecules to form chlorine, hydrogen and hydroxide. And then obviously with our sodium ion, which does not take part in the reaction, which makes it a spectator ion, we can then see that our net or our overall reaction is then 2 sodium chloride molecules react with 2 water molecules to form chlorine gas, hydrogen gas and sodium hydroxide in its aqueous form. It is important to be able to determine when there are multiple ions present. It is important to be able to determine which ion would undergo an oxidation and which would undergo reduction. In this case, that is easy to determine because we know, since water is lower down on this table, that it would more easily undergo reduction than sodium, which makes our water the reduction reaction and sodium the spectator ion.